So welcome back to the second part of the lecture, and we have these wave function. This is potential. We have energy parameters, and I don't need any of these equations, so I remove all of them to have space for making other calculation. Okay, before going further, we need to use another very good thing that we already know from one of our videos on parity of operators and parity of wave functions. We learned there that for a symmetric potential, and obviously this is symmetric within the well to the positive side of x is equal to 0 and to negative side of x is equal to 0, we have the same potential. Potential is V naught, so that means we have V positive x equals V minus x. When this is the property, we say that this is symmetric for both positive and negative value of the space. So this is a symmetric potential. Now, we learned that for symmetric potential, the wave function has the property of even and odd parity. That is, the wave function would be the wave function has definite parity, even or odd. And if we look into this equation, they are lacking of this property. Sorry, I should put a minus over here, right? Minus x. So if we replace x with minus x, we would have this situation. And if we look into these equations, all three of these wave functions are lacking this property. For example, if I put from 1, if I replace psi 1 in this wave function, x is minus. That is, we have psi 1x for minus x, and if I set x is equal to plus 1, I'll get psi 1x equal to exponent equal to b times exponent minus k. And obviously I'm placing x positive, and we know that we know from the definition of absolute that for positive value of x, x is just equal to x. So I'll put in x over here. But when I take positive value of x, that means I'm shifting from this region to this region, because the value of x are positive in this region, and in that region this wave function should reduce to this function psi 3, but we see that is not psi 3, and we can reduce this function to psi 3 provided we can have this behavior of the wave function, provided the integration constant b equals plus minus e. So if we replace this, then we have the definite parity in the form, this equation become plus minus e exponent minus kx, which is in fact plus minus psi 3 of x. That is, then by changing x from minus to positive, this wave function goes to this wave function. So this is then the wave function has definite parity, even parity for the plus value and odd parity for the negative value. So now we want to put this one wave function into definite parity, to possess definite parity, and we do this because when we have definite parity, when we have wave function of definite parity, it reduces our mathematical labor, because for that case, if I find the values at one boundary, the values of the other boundary are automatically produced from those values. So that reduces our labor, that reduces our mathematical labor. That's why we want to put this wave function as well into the definite parity. So these two wave functions with this substitution are now the function of definite parity, and we see that for positive value it is it has even parity, and for negative value it has odd parity. So this wave function is both even and odd for plus and minus value. And in order to put equation 2 or wave function psi 2, I construct a wave function of even parity. So I put in e over here to tell me that it is even parity in the form of half of psi 2 of x plus psi 2 of minus x. And if I put the values, I can write this in the form half into c exponent minus iota qx plus d exponent iota qx, and then I replace the same with negative values. So for this function it would become c exponent, so when x goes negative this will become plus. I write qx and plus d exponent, this become negative, so the exponent become minus iota qx. And from this I can write half into, now I take the positive exponent and negative exponent together, so I combine this with this term to write this as c plus d exponent minus iota qx, and plus I combine these two to write this as c plus d exponent iota qx. Since c plus d is another constant at this in this position, I define that to be equal to, I define c plus d equal to g, let's say. So I then write this equation in the form, and I take g common from this in this from the two terms to write this in the form. I write first this one, exponent iota qx plus exponent minus iota qx divided by 2. And you see this is the exponent form of cos function. So I write this as g cos qx. And obviously cos are even functions. So we have an even function in the form psi 2e equals g cos qx. This is even function and within the well, and I can construct an odd function by transforming this to odd OD. If I replace this minus sign, this plus sign with minus sign, that is, I subtract the two wave functions, then I would have a minus sign at this position and a minus sign at this position, right? These two would be the negative. And now, if I take the positive and negative exponent common from this and this, I can take this exponent common to write this as c minus d. Right? From these two terms, I would write c minus d. And from these two terms, I would write d minus c and then take a minus common to put them into c minus d. This would become minus. And similarly, this would become minus. And then I take c minus d common and I define c minus d as h. So that would give me h over here. And this would become minus. And now if you look, then this is sine function. So this is the exponent form of sine function. I write this as h times sine of qx. So here we have, I should remove this to complete the picture. I have this thing, psi 2 odd equals h times sine of qx. So now we have different sets of wave functions. I don't need this. I have I removed that somewhere, and I should have noted that psi 1x becomes plus minus e exponent minus k x, right? With a plus value it is even, and with negative value it is odd. So we have two sets of wave function. Even function, what are even function? Psi 1 with positive value, I would write there psi 1x plus, then I have psi 3 of x, and I have psi 2e of x. I missed writing x over here, but that is understood. So these three are the set of even function, and then I have odd function. So the odd ones are psi 1 of x with negative sign, this one, psi 3 of x, and we have psi 2 odd of x. So we have two different sets of function, and we want to analyze the behavior or the energy spectrum of these two sets of wave function. Since now these are wave function of definite parities, that means we can extract the whole of the story only by solving them either for this boundary or this boundary. And I want to carry the analysis for this positive boundary. And according to continuity of wave function, and I first want to do that for even function, according to continuity of wave function, the wave function at this boundary must agree with each other. So here we have this wave function, psi 2 of Ex must be equal to psi 3 of x. And if I put the values, I get psi 2e equals g cos qx, and this equals psi 3 is in fact equal to this thing. I put that e into exponent minus kx. This is one equation. And applying the condition on the derivative, I can write psi 2 e of x prime at x is equal to plus a should equal to, I should have put this at x is equal to a and this at x is equal to a. And then psi 3 prime of x at x is equal to a. They must be equal. And we can find the derivative of psi 2e. Psi 2e, if I differentiate this, we know the derivative of cos is sine, and then using chain rule, the argument will give me q. So psi 2 of this is in fact equal to, because the derivative of cos is minus sine, so I write minus g q sine qx. And I replace the value of x, which is a, so I call that qa, and that equals the derivative of psi 3 is in fact minus e times k exponent minus k, and I put the value of x, so that is a. I can cancel this with this, therefore I have gq sine qa e case exponent qa. Now again, if we look from the boundary conditions, we have the integration constant in this equation, the integration constant in this equation, and we can eliminate these integration constants if I divide this one equation with this equation. So we would easily get the equation g q sine of qa divided by this g cos qa, and on this side I will divide this e k exponent minus ka divided by e exponent minus ka. So what do I get? This g cancel with this g, this exponent and this e cancel with this exponent and this e, and at the end I would like to note it over here. At the end I have in cos qa, sine qa, where cos qa is tangent, so I write q times tangent qa equals just k. Wow, this is a very strong relation. You see, q is the energy parameter in the bound region, and k is the energy parameter in the free region, here or here. So in fact, this equation links the energy spectrums in the three regions of the space, that is within the potential well represented by q, and outside the potential well represented by k. So this is a very strong equation that provides us information about the correlation, about the link of the eigenfunctions of the Hamiltonian in the three different regions, or I would say in the two different regions, because the energy parameter in this are same. So this equation provides information between the correlation between the lengths in the eigenfunction in the eigenvalues or eigenspectrum of the two Hamiltonians in this region, and we will analyze that further. Now, what I do, this is the equation for even functions. And what if I do the same for odd function? For odd function, I have psi 2 odd. So I'll put this thing with 2 odd, right? And x is equal to a. And then psi 3x is again the same thing. And I would like to put the value here for psi 2 odd is in fact h sine, so I write that is h sine of qx equal to the same thing. And similarly from the derivative, I'll get the derivative of sine is cos. So from this I'll get I would like to rewrite this whole thing, and I would convert this to odd. So the derivative of odd function gives me h cube cos qa, because the derivative of sine is cos, and then it extract q from the argument. And on this side, I would again have minus k exponent minus k a, because I'll replace these values. And now again, I have two equations for the odd function, one this one equation and the other this one equation. And I missed writing e side. There is e. Let me write the e as well. So I have k e exponent minus ka. And in both equations, we have the integration constants. H is integration constant and e is integration constant. And I can eliminate these constants by dividing this equation with this equation. So if I divide this equation cos qa with this equation, I'll get h sine qa, and on this side I have this thing minus k e times exponent minus ka, and on this side I have e divided by exponent minus ka. So this cancels with this whole thing, this h cancels with this, and cos qa divided by sine qa is in fact cotangent. So I write q times cotangent qa equals minus k. This equation links the energy spectrums in the two regions for odd functions. So this is also this also carries the same information like this one, but this is for even functions and this is for odd functions. Now, both of these equations are transcendental equations, and we cannot further analyze them analytically. So for such equation, the strategy is to analyze them graphically or numerically, and we can analyze them graphically very easily. And we want to see, since this is the energy function or the energy spectrum according to this one equation in the free region, I'll call free region where potential is zero, and q is the eigenfunction in the bound region, and this equation links the eigenfunction or link the eigenspectrum in the free region with the bound region. We want to see whether all the possible values of k in q are acceptable solutions, or we have some other story. We want to visualize that. But before coming to that, I have another very beautiful structure, geometrical interpretation of these two equations. What if I square this equation and this equation and then add them to each other? So I don't need these things anymore. I would like to record these two equations over here. I have q times tangent qa equals plus k, and q times cotangent qa equals minus k. So these are the two equations. The tangent one is for even and the other one is for odd. So I remove all these things. Now let me square this equation. I write k squared equals minus 2 me divided by h bar squared. in q squared equals 2m v naught divided by h bar squared plus 2m e divided by h bar squared. That is, I'm removing the brackets. I'm splitting the single term into two terms. And now I add these two equations. I can write k squared plus q squared. This would cancel with this one, and I'm left with 2m v naught divided by h bar squared. And you see, this is in fact the equation of a circle in the KQ plane. So that means we have different circle in the KQ frame whose radius are given by V naught, by the depth of the potential well. So different potential well would lead to different circles of different radius. So that means only those eigenvalues, eigenspectrums in the two regions are acceptable, which falls on circle in the KQ plane, satisfying with whose radius is given by the square of this thing, right? Because we have the equation of circle is of the form x squared plus y squared equals r squared. This is in the Cartesian coordinate plane. In here we have the energy spectrum plane, k plane and KQ plane. So this must be square according to this one equation. So we say that the radius of the circle in the KQ plane is square of this thing. With that in mind, we now want to, so one thing, only those values are acceptable which fall exactly on a circle of a radius this square. Okay. In order to carry our numerical or graphical analysis, what we do, we want, it is always easier because in the present case we would need to count the units. We transform these equations into, we want to write these equations in terms of a dimensionless constant, a dimensionless parameter, and that I can easily do because we know that the arguments of trigonometric functions are dimensionless. Therefore, q times a is dimensionless quantity, and I can write that thing over here. I define a dimensionless quantity as the product of qa equals y. From this, I can write q equals y divided by a. So this is q is in terms of dimensionless quantity, and obviously a is a parameter that describes width of the potential well. And similarly, I define another dimensional quantity in terms of this thing. I write 2m v naught divided by h bar square equals r squared divided by a squared, where r is again a dimension. This whole thing is dimensionless. So I can put this value of q and this value of this parameter into this equation to find k in terms of y and r. And that I can do by putting k squared plus y divided by a squared equals r squared divided by a squared. That is, I'm replacing this value for this. And from this I can write k squared equals r squared minus y squared divided by a squared, or I can write k equals plus minus r squared minus y squared divided by a squared divided by a, and this is square root. And since we have learned that k is always a positive real, therefore we drop this negative value and take k equals r squared minus y squared divided by a, and here is square root. I take this thing, right? Now, if I use the value of k and the values of q in these equations, I can write these two equations. I can put these two equations. I don't need these things, so I remove them. I can rewrite this equation in the form q equals y divided by a, tangent qa is y, so I write y, and this equals r squared minus y squared square root divided by a. I cancel a, so I write y tangent y equals r squared minus y squared square root. This is the equation describing the behavior of eigenspectrum in terms of this dimensionless constant. And similarly, if I put the values in this one equation, I get q is in fact y divided by a, cotangent y equals minus k, so I'll put this value r squared minus y squared square root divided by a cancel with a, and that gives me y times cotangent y equals minus r squared minus y squared square root. This is the equation for odd function that describes the behavior of the eigenspectrum of those wave function. So now I don't need any of these things. I just want to plot these two equations and see what happens. What are the eigenspectrums for the two wave functions? So what I do, I take y-axis along horizontal like this, and along vertical I would once take y tangent y, that is along vertical I would first take tangent y, and then I take the values pi by 2, then pi, then 3 pi by 2, then 2 pi, then 5 pi by 2, and so on. I take vertical lines like this, like this, like this, and I take along horizontal y. And if I plot this side of the equation against y, I get curves like this for different value of y. These are the asymptotes. So then for this, it goes like this. For this, it goes like this. And now I again plot this side of the equation, that is I plot this thing, square root r squared minus y squared along vertical. And if I plot that for different values of r, I keep r constant. So I take, let's say I want to take two values of r. One, I take r is equal to r1. If I plot for r1, I have a curve like this. For a fixed value of r, I have this curve. And then I take this with another r. Let me call that r2. This is another value of r2. And I plot that against y, this thing. I get a curve like this. Right? This is a curve, a spherical curve like this. So now, this equation is true for which this side, the value of this side is exactly equal to the values of this side. And we see for different value, the two side agrees, because this is the point at which for R1, the two curves agree with each other, intersect with each other. So the corresponding value of y agree the two equations, the corresponding value of r1 and y make the two sides equal. Therefore, this is a valid value of the energy eigenfunction at this point. The other values are not relevant. And when I increase the value of r, I then have one here, and one here. Then these points at which the two sides, the curves corresponding to two sides intersect, are the acceptable values. So we see now if I keep on increasing r, that means I am increasing the depth of the potential, because we have written r equals 2mv naught divided by h bar square. I think whether it's a square or not, I don't correctly remember. Yeah, this is square. So these are constant, therefore increasing value of r means we are increasing the depth of the well. So when we increase the depth of the well, there are more bound states. These in fact give the allowed energy level, so these are different bound states. And when we decrease value of R1, that means we are decreasing the depth of V naught, so the number of state decreases. Even for R very, very small to I would have a curve like this, there is a bound state. That means for shallow potential, even for very shallow potential, we always have a bound state corresponding to even parity, because these are the plot for even parity. And if I plot for this case, if I plot this equation, the two sides of this equation, that is, I plot y cotangent y in this thing. So with vertical, I would have y cotangent y and then minus square root r square minus y square. I would plot these things along vertical, and here I would have y, and then again I would have pi by 2, then pi, then 3 pi by 2, then 2 pi, and then 5 pi by 2, and so on. I again take vertical lines like this, like this, like this, and the plot of cotangent y starts from pi by 2. I would have something like this. These are the asymptotes. And then for 3 pi, I would have a plot like this. And then for 5 pi by 2, I have a plot like this. There would be another point, which is 3 pi. In fact, at this position, so we will have 3 pi like this. And again, if I plot this thing, for R1, I have something like this. However, if the value of R1 is lesser than this value, I may have a plot like this. And then if I increase the value, I would have a plot like this, and so on. Okay, now again, we see this is important for not for all possible value of R. There is obviously no intersection of these graphs with this circle. So the R functions doesn't have solution for all possible value of R, but there is then bound states for R function as well, and the number of bound states increase the number of bound state increases with increasing value of R. This is, let's say, R1, this is R2, and I call this R0. But there are some values of R for which the R function has no bound states. We can make further analysis like this and can prove that when the depth of the potential becomes infinite, the eigenfunction reduces to the eigenspectrum reduces to the eigenspectrum infinite potential well, and we can do some other analysis as well. But that's the bound states, and we see that the bound state depends on V naught. So increasing the depth of V naught results in more bound state. In reducing the depth of V naught, we have little state. And for even function, there is always a bound state, and for odd function, there may not be. There is no bound state for certain value of potential V naught. And thanks for watching.